looking at these questions, under what conditions does the Schrodinger equation produce spherical harmonics as solutions? The condition is simple, but obviously important, and that is if the potential energy function is only a radial function. So I'm going to put here spherically symmetric. Different way of writing this equation. V parentheses R means it's a function only of R, or it's spherically symmetric. At least now that I've said it, I didn't look at your answers. I don't know if you guys nailed it or not. Does that ring a bell? So those spherical harmonics, they're the ones that work for a hydrogen atom or any other atom because, well, any other atom that we can solve with only one electron because it's spherically symmetric. Then the rest of these have to do with N, L, and M. So mathematically, where were the quantum numbers introduced?
Well, we're applying the theory to the hydrogen atom. Originally, they were just like dummy variables, but then we realized the relationship back subbed in.
Okay, that's exactly where it was. They were dummy variables that were introduced when we were trying to untangle our Schrodinger equation because we had an equation that was a function of three variables. As we tried to separate it into an equation just of the radial and versus the angular and then theta versus phi, that's where they were introduced. So that'd be when separating variables in the Schrodinger equation. Okay, then for the last two, well, the last three, because there was extra credit here. What do N, L, and M primarily tell you? Remember, I spent some time back there pointing at the periodic table, and N tells us the shell, which is primarily the energy level. So I would accept either of those, shell or the energy level. And as I pointed out, it primarily tells us that, but the other quantum values are also going to affect the energy. Otherwise, we would, remember when I was down there, I was pointing out that the D shell, or the D orbitals, D subshells, don't fill until you get down to the fourth row, where in theory, you should have had it in the third row. And so the reason it doesn't show up in the third row is that it must be a higher energy to put things in a 3D than it is to put them in a 4S. Okay, then L. What does L tell you? Or the total angular momentum. And M is the orientation. Well, orientation isn't perfectly correct. It tells you the component of the angular momentum in the z direction. And as the textbook, if you read ahead, which I don't expect that you did necessarily, it says, so can't we just align our angular momentum so it's all in the z direction? No, you didn't understand. We can't know all three coordinates, the x, y, and z components of angular momentum at the same time. So it doesn't tell us the orientation per se. It tells us about one of the components of the angular momentum. That's what it really tells us. I often say orientation. We often say orientation, but that's not quite right. But if you want to be specific, it tells us angular momentum in the z direction. So, any questions about the quiz? And the observation's like, that's only the 4th quiz so far? I did grade the 3 homeworks I was behind. I didn't get the current one graded. I did go far enough to find out, yes, I was wrong in class. And you know why I was wrong? Because I forgot to put a minus sign when I did the derivative. Right? You have the derivative of, that was for problem 4 on homework 8. You had the derivative of like g e to the minus kappa r over r, I think it was. And when I did the derivative, I had a positive sign for one of the 2 terms. It was because I did my derivative in my head instead of writing it out. So if I would have done this correctly, I would have had that, and then you see there's a minus sign in front of each term. That's where I had my mistake. I don't even remember which one I forgot it on, but I only put it on one. And it led me to heartache and pain. Let that be a lesson. Do your derivatives right. Okay. Any questions before I move into the lecture?
This is the last one.
I think there's one more. I know I said last week that it was the last one. I think there is a 10th one. I've got it open here because I have a 10th and an 11th here, but I do not think we're going to get to the 11th one for sure. Yeah, I have up through 11 made, but I'm sure we're not going to get to that one. Homework, well, forget it. Not going to look at it. But there should be a homework that it shows is due on Wednesday, right?
Yes.
Yeah. And remember, if you have questions on the homework, to come ask me. There were a number of questions that weren't completed on some of them that I was grading here. So if you have questions, come talk. I would much rather you have full understanding and high grades than being a little confused about the homework and not getting the high grades. Okay, I'm going to jump straight to this picture because I have it. This is actually kind of the capstone of where we're going to be going today, but it ties into what we had in the quiz. What we had in the quiz was questions about things we've already talked about that we are going to go through and cement in today. And so the L we said tells us total angular, L tells us total angular momentum. And that's the actual equation. The angular momentum squared is h bar squared times L plus 1. So, of course, if I square root both sides, I get L. And if you look in this picture, you see right here, L is equal to square root of 6 h bar. Right away, you can say what value of L you have, because that means L times L plus 1 is 6. 3 times 2 is 6. So that means L is 2 for this picture shown, and you can see that's written down here at the bottom. It's very hard to see because of the low resolution here. So this picture shows the total angular momentum as that kind of magenta arc. So I have an electron that's orbiting the nucleus. I don't know anything about its path, but I know that it has a total angular momentum of square root of 6 h bar. And then we have learned about the commutator relations that L squared will commute with Lx and Ly and Lz. We did those in class last week. But the Lx does not commute with Ly or Lz. Ly does not commute with Lz. So I can simultaneously know L squared and one of the three components of angular momentum. The other two I cannot know at the same time. I can only know one component. The other two, what that means is angular momentum is three-dimensional, and I'm not going to spin because I don't want to hurt my knee again, but I can know what the angular momentum is in one direction, and then I can tell you what the magnitude is that's perpendicular to that, but I can't tell you how much is in either of the two directions. And as we'll see later, it actually will precess around, according to quantum mechanics, as a function of time. So this here is showing then the z direction, which we arbitrarily choose one direction that we can find the component of angular momentum. And as you'll see, it's chosen to make life as simple as possible. So the angular momentum in the z direction now, what you see in both of these, h bar is the unit of angular momentum. You have 1 h bar, 2 h bar, 3 h bar, etc. for the component in the z direction. And for your total, you have, well, if L is equal to 0, you have 0. If L is equal to 1, you're going to have square root 2 h bar. If L is equal to 2, you have square root 6, and so on. When we went through the math of finding the spherical harmonics, we found the requirement that m had to range between minus L and plus L. So since Lz, the z component is going to go from minus L, so in this case minus 2, so I'm going to have Lz could be minus 2 h bar, minus h bar, 0, h bar, and 2 h bar. Those correspond to m equals minus 2, minus 1, 0, 1, and 2. So m could have any of those values, which means the component of the angular momentum in the z direction could be the values that I showed in this middle line. I'm going to make these components just in a different color. They'll stand out that way. So those are the possible values of angular momentum in the z direction you can have. And so on this graph, the dashed lines are indicating the possible values that your z component of angular momentum can have. And then, for Chad, this is more recent than for Aaron, but if you think about things like the phasor diagrams we did when we were talking about resistance and impedance and, well, resistance, reactance, and total impedance, we know that the total angular momentum must be the z component squared plus the xy component squared. So here we have drawn, here's the z component, here's the xy component. We just orient it so we make it so this direction here is the xy. You could call it the x, you could call it the y. No one's going to care because you don't know how much is in the x, how much is in the y. You just know how much is in the xy direction. And so this is the xy component, this is the z component, and then this is the hypotenuse. You can find out right away, since this is minus 2 h bar, and this is square root 6 h bar, you can use Pythagorean theorem to find out how long this is. Right, the 6 minus 4 is 2 square root 2 h bar. But it also gives us something interesting. That means that if we're in the m equals minus L, well, in this case, m equals minus 2, we can actually calculate the angle between the total angular momentum and our z direction using trigonometry. We have the adjacent side, we have the hypotenuse. So I can find this angle that's shown right here as theta by using cosine of theta is L sub z, the adjacent side, over L, the hypotenuse. Notice these H bars are just going to cancel for me. So I can calculate what the angle between my z-axis and my actual angular momentum is for each of those L values. So this picture is illustrating exactly what the M tells us. And pretty soon we're going to call it M sub L. Every time I say it, I want to say M sub L, because this is the angular, or excuse me, well, yeah, angular works. It's the M associated with L, with the total angular momentum. We are going to, tomorrow probably, have spin, and then we're going to have an M sub S for the orientation part of the spin. Do you understand this figure? No? Okay, so without spinning, I will still try to illustrate this. First of all, what does the z direction mean? It's arbitrarily chosen. It only comes into play if we put our particle in an external magnetic field. So if we put our particle in an external magnetic field, we define the direction of that magnetic field as the z direction. And then you can measure how much of the magnetic field is parallel to, or what the magnetic moment of your orbital is in the z direction. Magnetic moment is, well, it's telling us how the magnetic field of our orbital is aligned with the external magnetic field. And as you've learned, if I have magnets aligned, you're a lower energy state. Anti-aligned, you're a higher energy state. So if I put something in a magnetic field, it should try to align with it. But the quantum mechanics says that's not an option. It's not possible for me to have any magnetic field and have the magnetic moment align with it, which is really weird. Because in classical physics, that's exactly what's going to happen, is it's going to align. But quantum mechanics says it can't align. And the stronger I make the magnetic field, the faster it's going to precess around the axis of alignment. So if I make a weak magnetic field, it'll go around like this. A strong magnetic field, it goes around faster. So this is showing the different orientations of the magnetic moment. Just when I say magnetic moment, just think of my electron orbiting the nucleus is behaving like a bar magnet. You know, if I have a charge going in a circle, it makes a magnetic field. The right-hand rule tells you the direction of the magnetic field. This has angular momentum. We don't know what path it's taking, but we know the angular momentum, and that equation works with angular momentum. So if it's a fixed angular momentum, it's a fixed magnetic moment, even if it's doing some crazy convoluted pattern with that angular momentum. So anytime we talk about this magnetic moment, which the only reason we know anything about angular momentum is from magnetic moments, think about it as a bar magnet. Okay, so this is the upshot of what we're going to see today. So let's get started now at the beginning. Now, we've already gone through these first few slides, so let me zip past them. These are to remind us how we found the angular momentum operator. And we defined a ladder operator, which looks like a ladder operator because we have A plus or minus IB, which is similar to what we had with our other ladder operator. Not the same, but similar. What makes it a ladder operator is that it's going to do what a ladder operator does, raise and lower something. And then we did commutator values, so we found Lx, Y, and Z, these here. So we did those out carefully. I don't think we did this carefully, did we? We started on it. I don't think we finished it. I'm trying to think. Well, L squared is equal to Lx squared plus Ly squared plus Lz squared. And so if you do L squared comma Lx, that's equal to that's the first step in the commutator. And then we can immediately say, okay, Lx squared and Lx squared Lx, those are both Lx cubed, so those will subtract away. And so I have there's the two that match. And those two that match. And so now if we take this, we can say, better stay with the color here. If I take this, I could take, and this, I'm only going to do the red one now that I put down in blue. Because the other one, you can see it's going to have the same fundamental relationships. And so if I do that, I can say, well, Lx, Ly, because of our commutator relationship that said Lx, comma, Ly equals IH bar LZ. Then Lx, Ly minus Ly, Lx equals IH bar LZ. Therefore, Lx, Ly is equal to Ly, Lx plus IH bar LZ. And so putting that in, I'll put the Ly outside instead of inside. So that's what I have from the blue thing when I expanded the LXLY. So that's equal to and that should have been a plus sign when I put the parenthesis. I put the minus sign originally because I had them separated, but then when I combine them, I need to expand it. And LYLX minus LXLY, well, that is just going to be minus IH bar LZ. Is that right? LY, yeah. Now, if you look at this, you probably can get to the end. Minus I h bar times. Did I get anywhere? Yeah. So now that I have it down to here, Ly Lz plus Lz Ly, I can use a commutator relation to simplify this to having only one commutator. Then I have to go through and do the same thing on this one. I hope I didn't make any mistakes. And when you do the same type of work here, you should end up with this giving you minus what you have there so that they add up to 0. And yeah, I could have sworn that I did do this on Wednesday, but yeah.
You didn't get all those through.
Yeah, I didn't get all the way through this, just like I didn't get all the way through here. Do you see any obvious errors just before
So you're saying you can simplify the LYLZ plus LZLY?
assuming I made no mistakes, yes.
But they're both plus. How do you?
Okay, so yeah, that's where I worry about making a mistake because they're both plus. I'm going to assume I didn't make a mistake. So the first term, okay, I can't remember from 1 second to the next. This is Ly squared minus Lx. It was LYLZ, right? LYLZ. So that's what we found from the preceding page. So now let's do the second one here, come on, which is Lz squared Lx minus Lx Lz squared. That would have been too easy. That's a Z. It won't let me put it there because I'm too close to the margin. I hate that. In this case, I do have opposite signs, which means one of the two cases I have to have done it wrong.
Why were you able to move the LZ out to the front?
Which are you talking about?
So your third line, your LZ times IH bar LY minus IH bar.
Okay, so I have this. This here is that. That's the commutator relation. And then this here stayed the same.
How did you get the underlying correct part?
Okay. That was taking this term here is this one, and this term here is that one.
Okay, so the LZ that was on the right side is still on the right side.
Okay, so I have h bar squared lx is what I got for that one. So that means I did have to make a sign error here, because I should have had this a commutator relation, a minus sign there. So where did I make a minus sign error here? I could spend all day looking for sign errors we saw from my previous work. So at this point, sadly, we're going to have to kind of take on faith that I made a sign error. One of these should have a minus. So we can actually determine which one should have the minus sign, because this has to have the opposite sign is the other one to make it add to 0. So if it's going to add to 0, this has to be, this one here has the wrong sign, which honestly, I'm not seeing where I made the mistake, but I did. I can, as you might well know, these kind of mathematical things have been solved ad nauseum over and over, and I'm just embarrassed. But what can you do? We have two more commutator relations here. We have L plus minus with LZ, and L squared with L plus or L minus. This one here, if we had done that one correctly, then this is a direct result. Because remember, L plus is equal to Lx plus I Ly. It's a very funny way of writing a plus sign, or Lx. Going back just to make sure, L plus is Lx plus ILY. And so if L plus is Lx plus ILY, then this commutator is going to be L squared. And since these are 0, then each one of these is 0. So that one's really simple. This one here is a little more complicated because we have LX and LZ and LY and LZ to deal with. So let me do that one as a final commutator, show that I can do a stinking commutator. And notice I'm only doing with the plus sign. You can repeat with the minus sign and you're going to have the same essential work. But looking at our already known commutator relations, so if you look here, I separated it into two commutators. And then this commutator is known to be minus IH bar LY. That is, since LXLZ is IH bar LY, then LZLX is IH bar LY. Then if you reverse the order, it changes the sign. And so that's all I did to get the minus because it was XZ, whereas this was ZX. So that's why that's minus IH bar LY. This one here, LYLZ, is positive IH bar LX. To keep that in your head, if they're in alphabetical order, using a modular math, so after Z comes X, then it's going to be positive IH bar and the missing L. If it's in reverse alphabetical order, it's going to be negative. So LXLZ is reverse order because that's going from 1 back around to 3 instead of going from 1 to 2. And then I just factored out the H bar first, and then I times I is minus 1, so that's why I have minus LX. So I brought this term here. And then minus I LY. And then for the final step, factor out the minus sign. So L plus LZ is minus H bar L plus is what I found. Which really is supposed to be minus, or no, it's supposed to be plus. Did I write this wrong? Because it's kind of hard to screw that up. I mean, I'm doing it to show that I know how to do a commutator here. These are all summarized for us in the textbook as well. Page 166. And 166 doesn't have the ladder operators. Great. Oh, there it is, K. Yep, equation 4.106 on 162 says that I have a sign error again. It says that this here in the box is correct, which means where in the world, how do you even mess up a sign in this? LX, LZ, minus IH bar LY. Oh, I see what I did. Let's go back and. Okay, so this here is backward. Whew. I did my work right. should be minus plus rather than plus minus. These are in opposite order from what they are in the textbook. And I didn't notice the order. Well, I feel a little better. Not a lot better, but a little better. So we did this calculation. There, now correctly. And the lower one I didn't do correctly, and I'll figure out where I made my sign error eventually. So with those, we can recognize two things from commutator relations. Because L squared and L plus minus commute, what does that tell you? Okay, you can simultaneously know them both is what we've said every time up till now. Now we're going to take that same meaning and apply it differently. So it's not like that's wrong or partial. If you have two operators and they don't commute, that means when one is applied, it's going to change the other. And so because L squared and L plus or minus commute, if I do the L plus minus, it's not going to change L squared. But because L plus minus doesn't commute with LZ, if I do the L plus minus, it's going to change the LZ value. It's fundamentally the same thing. It sounds very different, but it's fundamentally the same thing as saying you can know them simultaneously. So what that means is the L plus minus is not going to change the total angular momentum, but it's going to change the component in the Z direction when we apply it. And so that is the essence of a ladder operator, that it's going to change a value. And now the next steps are rather convoluted. I am going to skip the math. This is explained the words I just said. I'm going to skip over the math of how this was done. Well, I'm not going to write it out. I'm just going to go through the salient or the important pieces. So given that L squared, L plus minus is equal to 0, then if I have this operating on a wave function, L squared, well, I've taken this to say then that actually I want to put that in a different color. That's what a commutator relation means, right? And so L squared, L plus minus psi LMN is going to be the same as L plus minus L squared psi LMN. But L squared psi is going to give me an eigenvalue. Oh, shoot. Really? I took that long doing math? I'm glad somebody knows, paying attention. Well, lambda is the eigenvalue for L squared. Because we haven't established yet mathematically that the eigenvalue is h bar squared times L plus 1, that's why we have lambda there. And then moving through, I'll have to pick up here. Figure out what I did wrong, pick up here.